All right, recording is rolling. So it is Monday, November 7th. A bunch of you guys just turned in your both your energy homework and your energy quiz. So thank you for doing that. And so we're going to start on a new topic today, which should take us all the way to Thanksgiving break. So this is going to be momentum and momentum conservation. Momentum is mass and velocity. Today's going to be a notes day. Give you guys a bunch of notes on how this stuff works. And it's usually involved in collisions. This is Unit 5 by AT's book. So I opened the next progress check over last weekend. Now this due 1 week from now. So when you guys come back in on Monday, then we'll go over the solutions to that. I have posted college physics problems to Google Classroom. Now it's having some technical problems with the printer over the weekend, so I did get you guys one printed page anyway, but this will print out for you guys real soon. But it is on Google Classroom if you want to see the college physics problems. All right, so if you want to try something a little bit different, so here's my schedule for the next 2 weeks. Again, it's going to take us to Thanksgiving break. I know it's real small font. Should print this bigger. Okay, here's what we got. And so I was looking in my lesson plans from the past. This is probably going to take us about a couple of days to cover all the notes that I want to cover. Right, so we've got some pretty cool labs. That I've got lined up for you guys. So a couple of them involve collision carts. So we've got like basically a low friction track, and these collision carts like bam, bam. You know, stack masses on them to change the mass. Right? And we're going to look at collision physics. Right? There's another lab I'm going to have you guys do that involves like a bouncy ball. That actually involves a property that AP's never been asked about, but I would always like to do in this lab anyway. So kind of bounce the ball at some point. Of course, we're going to go over AP Classroom Solutions. I have Monday slated for that. Now, how we do, you guys know I usually assign you guys some college physics problems. In fact, these are them right here. Right? And usually I go over them in class so you guys can see my thought process. But I think what I actually want to do with this one is the page that's on your desk right now when you guys walked in looks like this. Right? It's pretty straightforward plug and chug. And I think what I'll have you guys do is actually work in teams on the college physics problems, which I think you can figure out how to do based on this, pretty fundamental setup. Right. Oh, by the way, I've got the paper out on the other side. Well, okay, not that one. This is fine. The other page, but on the other side of your guys' page, there are here. There you go. Some conceptual questions that so get those help you out. I covered some of those. All right, and then I want to do an in-class quiz with you guys. That's what this red tile is. It says in-class quiz. So I'll have a quiz ready to go, and then we'll do that. Because of course we'll be going into Thanksgiving break, which is like a whole week off. So I don't need to give some guys with homework. I mean, if you guys want to take some time over the break to study extra physics, and that's only gonna help you out. But don't give everybody a bunch of assignments. So we'll knock that out Thursday, and then Friday. If anybody missed Thursday, then you can just make it up Friday. But otherwise, I need to line you guys up with an FRQ. So that's my plan. Of course, this coming Friday is Veterans Day, but you know what? We might not even be at school Thursday. I don't know. But you guys see that there's a tropical storm headed our way, like straight at us. Right, so there's a good chance that we actually won't be at school Thursday, but we'll see. Time will tell. All right. So anybody got any questions about organization or what's out there? Again, I do need to get you guys some more printed pages, but anytime, because that's coming soon. Okay. But everything's on Google Classroom, and there's an AP Classroom out there. All right, you guys good? All right. So, wait, before I write down any notes here, let me go and kickstart this with a video demo. Well, actually, here, I got a few. How about this? So here, all right. So here's Newton's cradle. Of course, I got this demo in class 2. Okay, so some kind of collision's going on. You guys see that? Now that right there, you're looking at a very special kind of collision, which is like pretty close to as bouncy as you can possibly get, which is called like perfectly elastic. Right? So not only is the general conservation of momentum collision physics going to apply, which would always be true. So when we get to momentum conservation, like so suppose you made those out of like clay and they stuck together, like, right? That would be the opposite of like bouncy, right? But also what's involved with a bouncy collision is, right? Since we just finished energy, you guys know one type of energy is kinetic energy. And that's what's also conserved in like a super bouncy collision is kinetic energy, which would not be true if those were made out of like wet clay and they were like something like that. Right, so we're going to look at collision physics. We're eventually going to do right, some bouncy balls. Right, that's this is a real fast demo. But do you guys see? Back up here. You guys see a basketball and a tennis ball. Okay, now you guys probably know whatever height you start a ball from. If you just drop the ball by itself, it could only bounce up to that height. It couldn't go any higher. Right, but here, take a look here. Bam! You guys see that tennis ball shoot way off, like higher than it started. Right, so it's probably getting some kind of property from the basketball. I mean, I guess you could say something about energy that would also be true, but since there's collisions involved, right? Anytime there's a collision involved, you're gonna have to use the physics that you guys are gonna learn like starting today, like this week. Right? Here, got an extended version here. There's a little either ping pong ball or golf ball on top of that, so it's a little bit more dramatic. Bam, something like that. Ooh, a really classic problem that I want to do with you guys eventually is a ballistic pendulum. So if you fire a bullet into a block, bam, it's going to swing this pendulum up to some height. Hey, do you guys see a height change there? You guys had a whole question on your take-home quiz about like pendulums, and there's some height change, right? And that height change it goes to would actually come from the speed change, like the post-collision speed of that bullet embedding itself in the block, which has something to do with the original speed of the bullet and also something to do with the original mass of the bullet. Right? So you could use this ballistic pendulum. Okay, let's run this animation again, right, to calculate what is the firing speed of the bullet. That was an old classic way to do it. Like, how fast can this gun fire? Right, well, if you know the mass of the block and the mass of the bullet and how high it swings up to, then it's all there, right? All you have to do is know the physics. Again, there's definitely some kind of collision going on between the bullet and the block, right? And do you guys think that during that collision that a lot of the wood is like being pressed out of the way, right? And maybe the wood's like heating up, right? So there's whatever the kinetic energy of the bullet was, well, a lot of that energy is being diverted into like force times distance of pressing the wood fibers out of the way and thermal energy of heating the block up, heating the wood block up. So it's really hard to solve this just in terms of energy conservation, which we spent the last 2 weeks doing. Okay? So you need collision physics, conservation momentum, which again, we're going to start today. Okay. And finally for you guys, okay. Oh, come on. No. All right, apparently this is gonna play this way. New video player. All right, Magic School Bus clip for you guys. Have I shown you guys this clip yet? Right. Okay, yeah, see this. All right, so this is an episode where they go into the textbook. Look, they're in a textbook, right? They're on a frictionless field. Oh, look at that, frictionless field. Physicists full of joy all over the world. Look, do you guys see how they're having trouble maintaining balance, right? That would be true, wouldn't it? Like if there was no friction, like it'd be really hard to maintain your balance. If you guys ever been ice skating, right? You guys know that was a low friction environment, right? Now, what I really like about this is when they start throwing this ball around, right? All right. Row it. All right, so she throws the ball forward and whoa, gets kicked backward. That probably reminds you a lot of which law of motion? Why would she get kicked backward? The third law, most I'm thinking, right? So for every force, there's an equal and opposite reactive force. There's a force between her and the baseball, and it's pushing opposite ways. Now, which is moving faster, the baseball forward or her backward? Baseball forward, because the baseball has a lot less mass, a lot less mass, which means during that force, now the force only acted for a tiny time interval, right? Maybe a tiny fraction of a second, right? The baseball was accelerating more, therefore achieved a higher final velocity, right? But see that all happened so fast, right? You could say, you break out stopwatch, you're like, bam, bam. Yeah, I mean, if you got the time right, which would be really hard to do, and figure out, okay, what was the force, what's the time interval? And you could go through all the physics that you've learned so far, and you could figure out how fast is the ball going forward and how fast she's going backward, again, if you know their masses. But there's there's a much faster way to figure out how fast are they going, which is what you guys are about to learn today, right? And what if you ran this film in reverse, right? So what if you film this whole thing and then you film this thing in reverse? It's not gonna let me. Right? You guys can match in reverse though, right? It's like the baseball and her head towards each other, and then like bam, it would look a lot like a collision, wouldn't it? Right? In fact, collision physics, the physics works both forward and backward, right? You can't really distinguish between the two. Well, except for one thing, and that's kinetic energy in the system, right? So thinking way ahead a few steps here, but how much kinetic energy was in the system when everybody was just at rest on the mound? She and the baseball were both at rest on the mound. How much kinetic energy? That'd be zero, right? Zero kinetic energy. And then she throws the ball and suddenly all this kinetic energy comes from, right? Hang on, Matt, I thought energy was conserved. Like where does all that energy come from? Well, in this case, it comes from places that we don't really account for in physics, like chemical energy, like the energy stored in our muscles, right? Right. That's where the energy came from. Right? We don't have a really good mechanical form of energy to express that. Right. Again, if you ran that film in reverse, there would be all this kinetic energy, and then bam, suddenly we go to zero. Like that kinetic energy would be like decreasing. Right. Again, it's not because energy is disappearing, but it would go to like other forms. Right. Right. So during all these collisions, there's usually a change in kinetic energy, with one exception, and that is, of course, if you have something like this, bouncy physics, right? Where that's the only one where kinetic energy would be conserved. And even then, it's not perfect, but it's probably as close as I can get. Okay. All right, so there's some ideas to think about so far. Switch back over. Okay, so we're talking about collision physics. Okay. So here we go. Right, momentum. Okay. So the symbol for this is going to be lowercase p. Okay. Sometimes I throw a little vector arrow over it. Not always, but that indicates that it's a vector, right? Okay. And momentum is mass times velocity. So in equation form, we go P equals mv, right? And again, sometimes I'll throw a little vector arrow over the vector quantity. Right? You guys know that's what that means, right? If you ever see a little arrow over a variable, it means it's a vector, right? So like the last couple of weeks when we were doing energy and conservation of energy, those were all scalar values, right? We almost never really talked about directions that things were going because you lost that information in the equations. Now you can solve things really fast sometimes, but that was the information you lost. But now we're back to direction is going to matter, right? So if you, so this is a vector quantity. So that you guys know that means that direction matters, right? And momentum conservation is usually used in collision physics. Anytime things are colliding, bam, you know you're going to have to do something with this. Okay? With the exception of usually if something's colliding with a spring, usually it's ignored, but anything else, right? If you ever see anything colliding, right? Or in the case like Wanda throwing the baseball and she was got kicked backwards because there was no friction, right? That's just a collision in reverse, right? Or if a grenade explodes, right? Again, if you run the film in reverse, it looks a lot like a collision, right? So anything like that we're going to use. Okay? So momentum is mass times velocity, right? Vector quantity, direction matters, used in collisions, right? And momentum is conserved in the universe. So you can say conservation of momentum. A lot like energy was conserved. Remember, energy measured in joules. Right? There's some quantity in a closed system that doesn't increase or decrease. Right? Same thing for the entire universe. Right? So we could set up equations in the last couple of weeks, like sum of energy initial equals sum of energy final, and then we could locate the different forms of mechanical energy, set up equations, and solve problems. Okay? Well, there's going to be something very similar here. I'm going to say the sum of, right? But instead of energy, I'm going to say momentum. Initial equals sum of momentum final. Right? And the initial and the final is really pre-collision, and post-collision. Right? So before the collision, there's still mass times velocity in the system. After the collision, there's still mass times velocity in the system. Okay? And that's always going to be true. It's always going to be conserved. Right? All right, you guys good so far? All right, so how can I expand upon this a little bit? Because that's a really general way of writing this. Right? Well, suppose you have a couple of objects. Okay? Actually, you know what's a really good thing to do is I'm probably just going to work off this page here. Right? So these are all some pretty straightforward problems. You guys see number 3? Right, we're gonna hop in on number 3. Okay? Those two objects collide head on, resulting in different measurements. What's the final velocity after the collision? Okay? And you guys see some formulas up in this box, right? So right now we're just focused on this first one. Let me zoom in here. It says conservation of momentum. I see mass times velocity of object A plus mass times velocity of object B, because that's what momentum is, right? It's mass times velocity. Right? So how massive is something in kilograms times v, velocity, how fast is it going, and also what direction? So think about it could be forwards, backwards. Right? Okay. So if you add up all the momentum bits before the collision, it's equal to the sum of the momentum after the collision, right? The sum of means like you're adding up all those bits. That's what that Greek letter sigma is. Right? Okay. So is that okay so far? Okay. All right. So this is just a really general case. All right, let's do. Now on my paper, I have this guy mass equals 1 kilogram. Now you guys have different paper than I do, but whoops, you guys can see this. Okay. And I have this guy mass equals 2 kilograms. Again, you guys have different numbers than I do. Right? You guys see your mass A and your mass B. Mass A, mass B. Okay. And they're headed toward each other. So all the problems on this page are just going to be problems in one dimension. Okay. Now you can eventually take these physics and take them into 2 dimensions and solve like billiards problems, right? There's a bunch of collisions going on with billiards, right? It's all in 2 dimensions on a plane. Right? We're just going to focus on 1 dimension. AP does the same thing. AP, yeah, usually they have just collisions in 1 dimension like this too. Okay. So, and if I see any exceptions to that, what is that? Okay. I have this guy moving with initial velocity, calls v naught for object A of 3 meters per second to the right. Right, so it's going 3 meters per second that way. And I have this object going the same speed but the opposite direction. So I'll call it v initial for object B. I'll go ahead and tag a negative sign to that, -3 meters per second, right, to show that they're going opposite directions. Is that right? Okay. Then these two objects are gonna, bam, they're gonna collide. Okay. And then what happens? Well, there's actually an infinite number of things that could happen, right? And it depends on the properties of these balls. Like if these were billiard balls or like Newton's cradle balls, when they like, bam, like bounce off each other really nicely. But what if they were like made out of soft clay? They went just like stuck together. I mean, that's possible too. And you wouldn't know just based on the setup. It could be either of those, right? But those are like extreme conditions. Those would be like perfectly inelastic and bubbling, perfectly elastic. Okay? Or maybe they're like, half deflated tennis balls. And they keep going, they kind of bounce off each other, but not very well. Right? That's possible too, right? So we're going to start setting this up, but you need one more piece of information before you can actually solve this. So let's start to set this up. Sum of momentum initial equals sum of momentum final. Yeah, this is before the collision and after the collision. Okay, so we're going to go mass of object A times velocity A initial plus mass of object B times velocity B initial is equal to mass of A times velocity A post collision final, okay, plus mass B times velocity B final. Okay. Like it's always this section. I just have a habit of like putting vector arrows up above the vectors. So I don't know, just a weird Griffin thing, I guess. Okay. You guys got that? If you don't do the little vector above the characters, that doesn't really matter. I'm just trying to emphasize they are vectors, right? So direction matters. So let's start plugging stuff in. Like I know the masses, right? I've got those numbers, right? And on your paper, and you guys got your own numbers too. Right? This page that you guys have. Extra notes for you guys, but so I'm not gonna pick it up from you guys, but so do what you want with it. So 1 kilogram feeds in there and there. 2 kilograms there and right there. Ooh, I have some initial velocities. Okay. So this guy was going in the positive direction, 3 meters per second. And this guy was going same speed but opposite direction, so I need to show that with a negative sign, -3 meters per second, right there. That goes together. Right? That's what the sum of me, that's the sigma. I'm adding up the different bits, just like last couple of weeks. Right? And then, okay, here's where, do you guys see like 2 unknown values? See, we don't know the speeds of either one of these after collision. So you see it sets up in an ambiguous situation, and it depends like, well, what are the material properties of these things? Like how bouncy are they? Right? It's called coefficient of restitution, which AP doesn't quite get into, but we will a little bit. Right, so here's where I told you guys last number you need to be able to solve this problem. I told you the velocity of object A post collision. Now my paper says -1 meter per second, which means that they were boing kind of rebounded off each other. So I need to plug that in here. -1.0 meter per second. I'll feed right in there. Okay. And now you guys see I have one equation, one unknown. This is solvable. I can solve this. What is velocity V post collision? Solve for that guy right there. Okay. That looks pretty straightforward, right? Okay. Got conservation momentum. Right? You're adding up all the momentum bits, mass times velocity, point. Okay. And then direction matters. Set up an equation. You guys can solve that. Okay. So let's see. I'm looking at 3.0 kilogram meter per second. Okay. Oh yeah, momentum doesn't have a named unit. So I'm just gonna call it kilogram meter per second, which is also sometimes called Newton seconds. It's the same thing, especially when we get to impulse, like a change in momentum. I usually call that Newton seconds, but kilogram meter per second, just this thing, right? So plus -6 kilogram meter per second is equal to -1 kilogram meter per second plus 2 kilograms times VBF. Okay. All right. I think you guys could do the algebra from there, right? So 3 minus 6 is -3, plus 1 is -2. Divide by 2 kilograms, you're looking at -1, right? VBF is -1.0 meter per second. Okay. Wait, double check that while you guys are checking yours too. 3 minus 6 plus 1, all divided by 2 kilograms. Yeah, -1 meter per second. Okay. So that working out on your paper too, you guys get one of the multiple choice answers. It's all good. Okay. Okay there. Now, I'm looking at my notes. I don't know how yours played out exactly, but it turns out that my collision actually is a special condition. It's a special case. What's special about this answer?
Negative.
Okay, it's negative, right? So it's moving to the left, right? You guys see these 2 speeds, two final velocities? Here's the final velocity of object A. Here's the final velocity of object B. Ooh, the fact that they're the same number tells you what happened during the collision. They stuck together, right? Right? Now, it didn't have to happen, right? But it happened to. You see it? Which means that this collision is perfectly, perfectly inelastic, right? Here, let's look at the 2 problems that I skipped here, number 1, number 2, right? Because these are 2 special kinds of collisions, right? Not all collisions fit into either one category, but right? So number 1 says 2 objects collide and boing bounce off each other so that the kinetic energy of the system is conserved after the collision. Okay, like Newton's cradle. That type of collision is, you guys circle elastic for number 1, right? So Newton's cradle, it's right here, boing, right? So not only is momentum conserved, which is always true, but also kinetic energy is pretty close to conserved. We'll call that elastic. So, right, but then number 2, 2 objects collide and stick together, which is exactly what my math is showing for my example. So that some of the kinetic energy of the system is converted to other types of energy. For example, 1 football player tackles another football player, right? 2 play balls stick together. Okay. So you guys circled inelastic for number 2. Inelastic. I see that. I see that. Right. Now, if that's really true, if some of the kinetic energy is converted to other forms, sometimes AP wants you to list those out. If it's an FRQ, it'll say, where'd the energy go? You say, well, there's a little kinetic energy left over, but what's missing probably went to permanent deformation. You could say heat. You could say sound. Permanent deformation they like a lot. You know, think about play balls, permanent deformation, right? Let's run a kinetic energy check on this one, because I want to show you guys that kinetic energy does in fact decrease. because it's easy to set up momentum problems where you accidentally get the time reversed. And it's like Wanda throwing the baseball towards home plate to get back the other direction. If you ran the film in reverse, right? In terms of momentum, if it's the same on either side, it's really hard to tell the time difference. But what can distinguish like an arrow of time, but which happened before and which happened after, is there should be less kinetic energy after than before. Again, unless it's perfectly elastic. Okay, so let's run the 1/2 mv squared. Well, I want to see if this is true. So I'm going to do, I'll just do this on a calculator. What's 1/2 times 1 kilogram times 3 squared plus 1/2 times 2 kilograms times, now -3 squared is still 3 squared, right? That be true? You lose a negative sign, but kinetic energy is a scalar anyway, so negative wouldn't even matter. Okay, let's see how many joules of kinetic energy we're there to start with. So I'm going to make a note here in pinky. Kinetic energy initial was 13.5 joules. 13.5 joules. Okay. Now after the collision, I don't know what it is yet, but I guarantee you it's less than 13.5 joules because I know it's inelastic. Right? It's got to be. There's no way it could be any. It can't be this number or more. It has to be less. Let's see. What's 1/2 times 1 times 1 squared? That negative just goes away. It's squared anyway. Okay. Plus 1/2 times 2 times, my final answer was same thing, so 1 squared. Okay. All right. So after kinetic energy final is 1.5 joules. Ooh, look at that. So it went from 13.5 down to 1.5. Okay. I see I lost a lot of joules of kinetic energy. Yeah, didn't disappear from the universe. It just probably went to like deformation mostly. Maybe like the sound energy of. Okay. All right. All right. Next one. Number 4. Actually, maybe I'll come back to this one if I have more time, because number 4 is the same setup as number 3, except I asked you for a pre-collision velocity. So if you're looking at things that happen after the fact, you must say, hey, what happened before the fact? Maybe this is a good thought process for like, if you're a forensic investigator one day and there's some car collision that happened and you're trying to figure out like who was going how fast before the collision. You can see some skid marks on the road. Okay, you say, okay, well, I have to solve for what was happening before the collision. Okay, but mathematically, it's almost identical to what we just did. Okay, just a general conservation momentum. Okay. Number 3, 2 objects collide and stick together. In a perfectly inelastic collision. Okay, so this one I am telling everybody, regardless of what paper you have, this is perfectly inelastic. Okay? Given the masses and initial velocities, what's the final velocity? Okay. Right. And I did give you guys a formula here. Perfectly inelastic. Now this is again a special kind of collision. This is like one of the boundary conditions, one of the extreme kind of bounces it can have. Okay. It's called the coefficient of restitution is 0, like perfectly not bouncing, perfectly stick together. And you guys see how you could just start from the general conservation of momentum and say, well, if they stick together, that means they have the same final velocity. So you could just factor that out. And that would look exactly like that, wouldn't it? Right, guys, that. Okay. So let's set up the pattern solver. All right, so we got what were okay, so I got mass A, mass B. This guy I'm calling 1 kilogram. This guy I'm calling 2 kilograms. Just looking on my paper. Your paper is different. Okay. And this guy has going really fast to the right. He's going the initial object A of 7.0 meters per second. And this guy's going kind of slow to the left. So velocity initial for object B is negative 2.0 meters per second. Oh, sorry. That's what kind of what you guys were imagining, right? Except your paper just said different numbers, but same thing, right? Okay. So we're going to go sum of energy, or not energy, sum of momentum. Sum of momentum initial equals sum of momentum final. Again, go like bam, like smack together right there. Okay. And the fact that you guys are told that it's perfectly inelastic, or if you're told like they stick together, right? Same thing. You could say, well, mass A, velocity A initial plus mass B, velocity B initial equals, right? And then you could set it up like we did before, but it's the same final velocity, so you can just factor that out and say, it's like they stick together and combine, make one giant mass. moving at one common final velocity, which is what we're solving for. You guys see that? All right. Now, when AP asks collision problems, if they ask any extreme condition, they usually tend to ask this one, right? Because the math is a lot more straightforward. It gets more complicated for bouncy situations. So we can do some mental math and get an idea before you even start plugging and chugging. Right? Do you guys see 7 units of momentum to the right for this guy? Do you guys see 4 units of momentum to the left for this guy? 7 to the right, 4 to the left. So when they stick together, who's going to win? The guy going to the right, the guy going to the left? I think the guy going to the right, right? He's less massive, but he has a lot more velocity. And when you multiply those two together, he has a lot more momentum going to the right. So overall, the system's going to go to the right. So this answer has to be positive, right? You guys see that? Okay. That's one of those good things to do when you guys are going about solving equations, saying like, oh, well, let me slow down, see the big picture. Say, oh yeah, this would be going to the right. Okay, so I must get a positive answer. So start plugging some numbers in. Got 1 kilogram going at 7 meters per second plus 2 kilograms going at -2 meters per second equals, and they're going to combine, make one giant mass of 1 plus 2 kilograms moving how fast? Okay. So we got 7 minus 4. Does that look like 3 units of momentum in the system? Okay. So this is 3 kilogram meter per second of momentum in the system. That's going to make a giant 3 kilogram mass moving at some final velocity. And my numbers just happen to work out really nice because I just 3 divided by 3. And the kilograms cancels. So final velocity for me is going to be +1 meter per second, which is 1 meter per second to the right. Okay. And again, before I started plugging and chugging, I said, well, it's got to go to the right because there's more momentum to the right. Okay, and it definitely is. You guys hear that? Okay, every right? Yeah, AP tends to like these types of collisions, these inelastic types. Okay. Well, let's do a quick kinetic energy check, because again, I guarantee you there's less kinetic energy after than before. Right, so let's do 1/2 times this m times this v squared plus 1/2 times this m times this v squared. Okay. I'm looking at kinetic energy initial is equal to 28.5 joules. How about after the collision? Okay, final. What's that? Well, that's 1/2 times the combined mass of 3 kilograms times the final velocity of 1 meter per second and square that. That's 1.5 joules. Wow. So guys, from 28 down, okay, so lost a lot of kinetic energy, right? Again, the energy didn't disappear. It probably went to mostly like permanent deformation of like splat, like force times distance of like remolding these things. Okay. All right. Okay. Next one. Ooh, number 6. Grenade flying through the air. Actually, let me do but before we do this one, you know what I should really talk about, because it's like the same problem, is Wanda throwing the baseball. Right, so you guys just saw a Magic School Bus clip. Okay. So let's have this situation going on here. Okay, let's actually solve the problem. Okay. So a little baseball hat. How about that? Okay. All right. Wanda throws the baseball to the left, and she gets kicked off to the right. Okay. Give you guys some masses. What's the mass of a baseball? Is it 0.145 kilograms? I think it's what it is. Does that look right? Okay. And what could her mass be? Probably like, let's call her 60 kilograms, maybe something like that. I don't know. Like 3rd grade or something. Probably less than that, but let's just run with it. Okay. And let's say she's going to throw the ball at V throw. Well, I'll call it V ball. How about that? V ball. So after she throws it, let's call it 20 meters per second. Okay. And the question is, what is B Wanda? Okay, how fast is she gonna get thrown back towards second base? Okay. Again, if there's a frictionless field, then she's gonna slide that fast towards second base. Okay. So let's do sum of momentum initial equals sum of momentum final. Okay. Because this is a collision problem just in reverse. Again, if you reverse the film, it looks exactly like a collision, doesn't it? Okay. But guys, when she's standing with the ball at rest on the mound, how much momentum was there in the system? Mass and velocity. Zero. There was 0 kilogram meter per second in the system. Right? There was nothing. Okay. So where did all the momentum come from? I thought momentum was conserved. Well, remember, momentum was vector, so it got to the left and to the right. Okay. So really, maybe this number should be called negative, right? Should call this like a negative number. So this could be a positive number, for example, or somebody has to be negative. So say equals to, let's just plug in masses and velocities right here. So we got mass of the ball, 0.145 kilograms, going at 20 meters per second. Yeah, I'll call this negative 20. How about that? Negative 20 meters per second. Okay. Oh, to the left. Okay. Plus, mass of Wanda, 60 kilograms, going at, well, we don't know how fast. Call it B sub. Yeah. That's what we're solving for. How fast? Okay. But you guys see how to solve this real fast, right? Just gonna add this over, divide by 60. Oh, 20 over 60, that's like a third, right? So 0.145. Okay. So do a little algebra here. Looking at 0.048 meters per second towards second base. So real slow. Because it's real small mass baseball. Okay. All right. Okay. Now, for something like this, is there going to be more kinetic energy before or after the throw? Yeah, this one definitely after, because there was 0 before. There's 0 joules of energy before. Okay, so which might seem weird, but remember, this energy came from somewhere. It came from her throwing the ball. Right, all right. Okay. All right. So I want to do this a step because that's a really good step up to solving the grenade problem, which is really like the same problem, okay? Except now the grenade's in motion, but momentum's still going to be conserved. Okay. So we got this grenade flying through the air. Somebody throws the grenade. Let's say they threw it this fast. The initial was this number. There you go. Right, this many meters per second. Okay. And then the grenade, bam, explodes into 2 parts. And one of the parts takes off going this fast. So the question is, how fast did the other piece go? Okay. So we can do kind of an extension of what we just did. This is number 6. Okay. We have like one grenade going at some initial velocity. Okay. And if you add the bits together, I told you the 2 bits, like after it breaks apart. Right? But do they add up to 1 kilogram on your paper too? Mine they do. It's like 1 kilogram. So it's like a 1 kilogram grenade going at the initial like so many meters per second, right, to the right. Okay. This thing's gonna bam explode into 2 parts. Let me see. So okay. I don't think it's the most realistic numbers, but the idea gets across, right? So one piece has to speed up. I'll call it velocity piece A final is like 20 meters per second. I'm just going to use the number straight on it on its page. Okay. Mass A, I've got 0.4 kilograms, and mass B, I have 0.6 kilograms. Okay, so 2 parts, bam. Okay. Now the second bit, maybe it explodes backwards, or maybe it just slows down. Right? But it has to be less than 15 meters per second. Right? It could be negative. It could be negative, huge number possibly, but right, mathematically it has to be less than this number. Right? So I don't know. You say some generic, maybe it's still going forward just really slow, or maybe it's actually kicked backward. Either of those is possible. We can find out with conservation momentum. Sum of momentum initial, say before explosion, equals sum of momentum after explosion, right? And if you film this thing and then ran the film in reverse, it would look exactly like a collision. Okay, so it's an explosion. Okay, so the initial momentum is just 1 kilogram at 15 meters per second. Right, so m times v naught. Okay, and then it explodes, bam, into 2 parts. One part is 0.6 kilograms, And that's going at, well, we don't know, dV final. And the other part is 0.4 kilograms going at 20 meters per second. Okay, guys see that setup? Okay. Now, I think that's 8. 8 I can subtract over, get 7 kilogram meter per second, equal to 0.6 kilograms dVF. Record 6. I'm getting this many meters per second. Okay. Something like that. So my grenade still happens to be like all the parts are going to the right, but just kind of slow down. Right? Is that okay? Let's run a kinetic energy check. Okay. Because again, this one I guarantee you there's more kinetic energy like after the explosion. Okay? Because that energy came from somewhere. It came from the chemical energy that was stored in the grenade to start with. Again, we don't have a really good mechanical way to express that in physics, but it'd be chemical energy, right? Bam, the energy of this explosion. Bam. Okay. So the initial kinetic energy, K naught, is, let's see, 1/2 times m times v squared. I'm looking at 112.5 joules of kinetic energy. Kinetic energy final, let's see, is 1/2 times 0.4 times 20 squared plus 1/2 times 0.6 times 11.7 squared. I'm looking at about 121 joules. Yeah, so the energy went up, and the difference in that energy would represent the energy from the explosion. Okay, all right. All right. There's more I want to say with this because a really good AP style extension to that is to say, well, where do the grenade parts land? So suppose somebody was like the trenches of World War I going on or something, right? And this guy takes this grenade and launches it. Right? He's gonna throw it like straight, so it would like land there, right? But it explodes like midair, like right there. Right. So if the entire grenade just like as one unit had landed, it would land like in this trench, something like this, right? Okay. But if the thing explodes, then we got different parts going different ways. And to keep it simple, let's say in this assumption was like baked into what we just did, is we were just treating everything in one dimension. So one part goes to the right, and one part either goes to the left or like slows down, right? Something like that. And the map I did like slow down, but still going to the right. Okay? So if you follow those individual bits, do you think that here, just keep it real simple. Suppose it was like exactly half and half. So you had a 1 kilogram guy and it splits exactly like 500 grams, 500 grams. Bam, 500, 500. Okay. Do you think that the two parts would land like equidistant from where they would have landed had there just been like one solid grenade? Like if one lands like 5 meters shy of the trench, the other piece like overshoots it by 5 meters, you guys think? Right? And then what if the masses are unequal? If masses are unequal, do you think that momentum is still conserved? So maybe the smaller piece would miss by a lot more and the larger piece would land pretty close, right? But if you do sum of momentum, right? See, like the center mass of this grenade still lands in the trench, even if there's no physical pieces to land in the trench, right? So the whole grenade could land in the trench, or the broken pieces, bam, could miss the trench. But if you found the center mass of those pieces, it did exactly the same point as if no explosion happened at all. You guys can get that? Right. That's a good AP style question right there. Like that could totally be something you guys could see on the AP exam. Okay. You guys get that? All right. Good so far. All right. Number 7. Please got any question? Any question? Because we're going to move on to this other kind of collision. Look at this, perfectly elastically. Two masses collide head on perfectly elastically. What therefore is the final velocity of object A? So, okay, I gave you the masses, 2 masses. Okay. Here. I want to make sure you guys have this visual for this one. Okay. So we're talking about 2 masses colliding perfectly elastically. Okay. That's pretty close to that right there. We're talking about like perfectly balancing, okay, which is like a boundary condition of collisions, right? That's like an extreme example. So I gave you each mass. I gave you their starting velocities. Looks like they're headed towards each other, like head-on collision. Again, we're just treating everything's in one dimension. Okay. I said, what's the final velocity of one of the objects? Now, at a glance, you might say, well, hang on a minute. I remember back when we were solving like number 3, I know we skipped number 4, but it's kind of the same thing. Okay. I had to give you like 5 pieces of information, right? 2 masses, and then like 2 velocities before, and then 1 velocity after, and then you can solve it. Okay. Or like number 5, you look like short piece of information, but I did tell you they stuck together. So you say, okay, well, they stuck together. Maybe that's the extra piece of information. So they have the same final velocity. You can just factor that and solve for it. So that's fine. We did all that. Okay. But now we're looking at this perfectly elastic, and it looks like I'm shorting you guys a piece of information again, right? But the fact that it's perfectly elastic means that now there is enough information to solve this system. Right. So let me show you guys real big picture how this works. And of course, you guys see this perfectly elastic collision setup right here. Okay. So if something is perfectly elastic, that means we care about 2 things. We care about momentum is conserved, sum of momentum initial equals sum of momentum final, okay, which is always true. That one's always true in the universe. But we also care about the sum of kinetic energy before equals the sum of kinetic energy after. Okay. Now, energy in general is always conserved, but not necessarily one type of energy. But in this case, it is. Okay. So energy and motion. Okay. See, I can set these 2 up in a system of equations. I can make a system out of these guys. Do I have here? I was going to put this in your notes, but I really just want you guys to see big picture on this. We got some new posters hanging up. So bam, there's general conservation momentum. We did that, solved that already. There's the perfectly inelastic collision. We solved that already. That was like number 5. Right? So common final velocity. Okay. And then there's this guy, right, that we're kind of in the middle of right now. So I can have the system of equations between not only is momentum conserved, which in general looks like this for 2 objects colliding head on, right? But also kinetic energy. All the 1/2 mv squared bits have to be also conserved, right? Like the sum of those, right? And there's a general solution to the system, and it's always this right here. Okay. No, there's a lot of questions we could go and like investigate this a lot more, but so the answer, right? Now, does AP ask questions about this? No, they don't expect you to memorize this. This would take a long time to solve. You might say this in college. There's a good chance college teacher might ask you to like solve this from scratch. By the way, this expression really hard to find in physics textbooks and also kind of hard to find on the internet. So hold on to these notes because this could save you a lot of paper and time one day in college possibly. But is AP going to ask about this? No, except if they ask something very simple. So every rare once in a while, AP asks something about an elastic collision. They'll say sometimes they just say elastic. They just say elastic, but they mean perfectly elastic. Okay. But they'll say something like, well, if the 2 masses are the same mass, right? Same mass. Right. And then one starts at rest and the other collides with it, let's say like 3 meters per second. Then wouldn't one object come to a dead stop and the other just assume the speed of 3 meters per second? Right? You guys see that? Because they would want you to have this model in mind. Right? Now you can confirm that with this expression, but you don't have to memorize or actually apply it. Like that. Right, is that okay, so far? Yeah, we're about to run to the bell here. All right, so again, tomorrow, give you guys some more notes, and then yeah, we will continue this adventure. Still got to tell you guys about impulse. Right, gotta get some labs lined up for you guys, and hopefully this tropical storm doesn't hit us, but time will tell. All right, so let's do a pause right there. 9:35.